Greetings and welcome to today's webinar, USB-C and PD compliance testing. I'm Mike Micheletti and I'm a product manager here for the USB testers at Teledyne LaCroix. Thanks for joining us. We have a lot of people on this broadcast, which is great. Not surprising that Type-C and PD are hot topics. There's been a big rush of development, really. Everybody wants to be first to market, and that can lead to some people taking shortcuts. There's been quite a few horror stories out there about misbehaving power supplies and cables. And that's why compliance testing is a top priority for the industry. Everyone knew that PD was going to require more testing, but what we didn't know was how long it was going to take to get the test specs done. So finally, the PD compliance plan is getting released later this month. The pieces are finally coming together. And that's the topic of our webinar. We've just got some of our last people logging in now, so we're going to get started right away. Today's agenda is going to be a deep dive into really the entire certification process. We'll walk through a dozen different PD test examples, focusing on some of the more critical tests. The Type-C compliance is a separate test spec. It's designed to verify all the logical state transitions for a Type-C port. And it's very ambitious. A lot of these assertions occur at the electrical level, so that makes them harder to test, harder to debug, really. There's a lot to cover on Type-C, so you'll probably see another webinar just on Type-C in the very near future. But stick with us. We'll announce the winner of our analyzer giveaway at the end of the webinar. So this is the advanced class. For the intro class, you'll want to view our Intro to PD webinar from last September. It's a good overview of the technology. Just search for webinars on the Teledyne LaCroix website to find it. We have a lot of material to go through. Of course, everyone will get a copy of the slides by email sometime tomorrow. And if you miss anything, don't worry. You'll be able to replay it on YouTube in a few days. It's real important that we cover any questions. So if you have questions, just type them in using the chat box. We'll try to get through as many as we can at the end of the presentation. Most of you already know that we have two separate specs, the Power Delivery 2.0 and the Type-C cable and connector spec. The PD spec addresses all the elements of the logical PD protocol like discovery, negotiation, role swaps. You'll find the electrical and mechanical requirements in the Type-C spec. So two separate documents, which is probably the reason we have two separate test specs. If you are a device with a Type-C connector, you're going to have to pass the Type-C functional spec. If you also implement power delivery, you'll need to pass the PD compliance plan. So starting with the PD compliance plan, the USB-IF followed a different path than normal with PD. The spec is really just a list of assertions organized around chapters of the base spec, including protocol and power supply. There's more than 450 assertions, half of which are not testable. For the remaining asserts, they decided to follow an MOI approach where the test equipment vendor defines their own method of implementation. And later this month, they're finally going to release these documents. Mostly everyone is following the MQP MOI because it focuses on the most important test cases. These are the tests that the USB-IF will actually use to determine if a device passes compliance. So what's required to pass compliance? This is a high-level summary. Of course, PD is optional, but if you go to a workshop and your device supports PD, you would need to pass the PD compliance plan. If it's a designated power supply, there's some additional tests required for PD power supplies. Virtually 100% of PD devices are using the Type-C connector now, so you'll also need to pass the Type-C functional spec. This is still considered draft at this point, but we'll be running our latest Type-C tests at the next USB workshop, so we're getting closer. Hopefully later this year, they'll actually start certifying Type-C end products. Right now, only PD silicon is getting certified at the workshops. Now, if your device only has USB functionality, or it also has USB functionality, it has to pass all the relevant USB compliance tests. So they've been certifying Gen 1 SuperSpeed for a long time. For Gen 2, the 10 gig devices, they're still considered beta or dry run at this stage, but they should have all the tests in, all the fixtures they need to start testing 10 gig, later this year. These are the key functional areas that are tested in PD. There's, of course, the protocol. There's cable detection. They need to test the PHY layer. If your device acts as a provider, there's a power supply section you need to pass. The policy manager stuff operates at the upper layers. This is really Chapter 8 and Chapter 9 of the PD spec, and this is mostly tested using software. There's a beta version of the USB-CV that has some of these tests implemented right now, but this is also not quite finalized yet. So as I mentioned, power delivery is an optional feature. You don't have to use PD in your Type-C device. You can rely on legacy V-Bus. But for devices that are PD capable, some will have more functionality than others, right? Not all devices are created equally. Within these different PD products, there's going to be different capabilities that need to be tested. Here I'm just summarizing the major areas for PD testing, and we'll look at a lot of these in a minute. And when we do, you'll notice that DRPs are subject to the most stringent testing because they have more functionality. On the other end of the spectrum, consumer-only devices are simpler. They don't need to do power roll swaps or data roll swaps. Basically, you can skip a lot of the tests if you're a consumer-only device. But at a workshop, we have 50 different devices walking through the door. How do we know what to test? We need to basically know exactly what a device's capabilities are to run the right tests. So for PD compliance, all vendors are required to provide a text file which describes the different features he supports. The USBIF has a little app called the PD VIF generator that walks you through all these questions. For example, each PDO needs to be specified. What's your max current? What's your operating current? Because we're going to verify that he can actually source or sync that level of power during testing. There are fields for roll swaps, VCONN support, does it send SOP prime messages? All of these fields are exported to a text file, which then the tester uses to run the test. So it's critical that this information is correct, not only because it's used by the test equipment to pass or fail a device, but it's also used by the USBIF to track the capabilities of the product or the chipset. So if you overlook a feature like battery-powered operation, then we won't test it, and it won't be considered certified for that mode. Also, say you bring a test board to the PlugFest and it has more than one configuration. You would need potentially to provide VIFs for each configuration. For example, if a device can operate with or without external power, you would need a VIF for each. So just to give you a clear picture of how this works, once you've created the VIF, you go into the Teledyne LaCroix compliance test software. Before you run any tests, you'll use the VIF button. It brings up a dialog where you choose Open File. You select the VIF for the device you want to test, and it will load into this window with all the fields clearly labeled. You can click on any field to edit it in this window, which is very handy for debug. Although during the formal USB workshops, you're not allowed to make changes once you've submitted your VIF. Almost every test we do relies on the data in these files, the VIF. And really, this is one of the most common reasons for failing compliance. When the VIF doesn't match the device behavior, you're going to get a lot of fails. So check this information carefully. Okay, so the PD and Type-C tests are only supported on our Voyager M310C, which has the native Type-C ports. You would just connect directly to the DUT over a short 5-amp cable. Setup is basically the same for source or sync. No special tricks, no special boards, although we do provide a custom cable for some of the Type-C tests. So we need VCONN to go end-to-end so we can check the voltage levels, the 5 volts, in some of these Type-C tests. But we'll cover that a little later. So the tester will use these settings during verification, as I mentioned. Back in the LaCroix software, what you would do is you would use this preset button to select the test you want to run. These are organized around provider, consumer, and DRP. So based on your device type, you pick one of these sets. Most PD chipsets that come through the workshops are full-featured DRPs. So you would select DRP. That'll bring up all the primary tests. You click Run, and it's going to perform each test automatically, generate a pass-fail report. Probably this looks really familiar. This is the same test environment that the USBIF uses for link layer in hub certification. All right. So now we'll get into the nitty-gritty of the different test implementations, starting with the message and protocol checks. So the original 1.0 PD spec used the term profiles to create sort of a standardized way of identifying power supplies. This was supposed to help educate consumers about what kind of power brick they would need to charge their device. But it was always optional for vendors to use these profiles, so a lot of early developers went off and did their own thing, and this was creating confusion in the market. So after a lot of discussion, they actually scrapped profiles. It's actually removed from the most recent spec, the newest PD 2.0 Rev 1.2 spec. They actually restructured the profiles into power rules, which is basically the same idea, only now they're mandatory. The idea here was always around making it easier to reuse Type-C power supplies. They want to actually make it simpler to use different bricks and make them more interchangeable, really. So the new power rules are targeted around, typical USB V-bus applications. Instead of profiles, there's a single parameter now called a PDP, which is the maximum wattage of the supply. The key change here is that it should be able to charge any device with a lower PDP, according to this table. So smaller devices, right, can still be shipped with a low-cost power brick, but a full-size laptop that ships with a larger power brick, it's got to be capable of supporting all these other devices. This is why they added the 9-volt rail, and really it's all around delivering a better user experience. If you just grab any power supply off the shelf, you don't want to burn up your device. Initially, the focus was on AC power adapters, wall warts. But as it's written now, it's required that all USB Type-C devices need to specify a PDP. So for ports that can act as a provider, we'll now check that he reports that all the required PDOs from this table. The backstory here is that they're trying to get IEC to endorse PD and Type-C. And in fact, just this week, it was announced that approval is now done for the Type-C connector. So in the future, really, to reduce e-waste, rechargeable devices, battery-powered devices, really, will have to use the Type-C to ship into Europe. So, that's huge. So all the power rules are verified in the test 2.1411, where we record the source cap message and then check all their PDOs. So using the PDT from that vendor info file, we'll verify the actual PDOs they send over the wire are actually consistent with the voltages defined in this table. So if a chipset has a PDP of 45 watts, we're going to verify that it advertises all these other required PDOs. It would need to support 3 amps at 5 volts, 3 amps at 9 volts, 3 amps at 15 volts, and 2.25 amps at 20 volts. So this guy reports the correct PDOs for a 45 watt PDP. But there's lots of older devices out there that don't comply with this clause. For example, here's a device we tested recently which has a 3 amp at 5 volt and also the 5 amp at 20 volt, but it's missing the 9 volt and 15 volt PDOs. So this would be flagged as a fail going forward. Now, because this is a new requirement just added at the January 2016 workshop, there's a 1-year waiver period. So you can get a waiver on this test for the next year or so. What about sinks? They also need to provide a PDP value in milliwatts, which is entered in the VIF in the sync tab. Here, this device is also reporting 45,000 milliwatts, so a 45 watt PDP as a sync, and that would be used during testing to identify the maximum operating current he should advertise. So I'll highlight the 3 most significant checks here for sync capabilities. 1, they shouldn't advertise a max current over that PDP. 2, if a source can't meet their minimum required current, the sync is supposed to set their capability mismatch bit. We'll check that. And 3, they must be able to operate at that PDP. This item 3 is not really tested. The only verification we can do here is make sure the sync makes a valid request for a PDO and completes a contract. So here's an example of a typical fail case. The 15 volt at 2 amp is valid, but the 20 volt at 3 amp is not. Looking again at the power rules table, we see that he's reporting a PDP of 45 watts. Well, 45 watts divided by 20 means he should not be exceeding 2.25 amps in this last PDO. So that's a problem. Okay. Different test, simple test here, where we just verify the contents of the message. A side note, tests that start with the prefix TDB indicates that it's a secondary test. You can run this test explicitly in our software, but we're also going to check these fields for every message we capture during a primary test. So we're going to check every message for proper format, kind of in the background. This is a Discover ID message, which a DFP would typically use to find out what kind of PD device it's connected to. We're going to make sure that all the fields are valid, like the command type should be set to 0, the object count should be 1, and the message type should be 0F. So these are all pretty easy. In the test 22101, we actually check the protocol side of the sync capability message. So this is more about testing the timing and the handshaking. It's a secondary test, but we couldn't run it explicitly. So the DUT sends his default PDO. We make a request. After the PS ready, we send a get sync capability, and really just to make sure he responds. The trick here is that this DUT is a provider only. So as a source only device, it actually fails this test. We're sending it a get sync capabilities. He needs to send a reject, but he responds with his capabilities message. A source-only device should never respond to a sync capabilities message. The root cause is probably just a board configuration issue. They had a dip switch wrong or something like that. Okay, cables and connectors. There are a handful of tests here specifically for cable markers, and they're all pretty simple, nothing too tricky. But one of the more critical tests for safety is TDA 2221, check cable capabilities. Looks like a cable test, right? But it's actually for PD devices. We want to verify that a source doesn't offer more than 3 amps on a 3 amp limited cable. So to complete this test, you need to use an E-marked cable. So that means it must have the chip that responds to SOP prime packets. But it should have a limited current rating of just 3 amps. It's not that easy to find a marked cable with only a 3 amp capability. Most full-featured cables we see have the 5 amp marker. So if you just grab any E-marked cable for this test, it's likely to be a 5 amp cable. The source will CRA and do discovery on the cable, and it would be perfectly valid for the PD source to then offer 5 amps. But then it would fail the test, right? So here we're trying to make sure he's paying attention to the capabilities of the cable and then limiting his source caps to 3 amps. So there's really 2 ways to do these tests. If you can get a 3 amp E-marked cable, we'll go through that. The PD source should advertise RP on his CC1, and then it would CRA on CC2, so it knows it's a marked cable. It will source VCONN, then send a cable message to discover its capabilities. The cable will respond to the discover saying, hey, I'm just a 3 amp cable. So the next thing on the wire should be a source capabilities, and within that message, the max PDO should be 3 amps. So he doesn't go over that 3 amp limit. Second way to complete this test, using our special unmarked RA cable. This is a custom cable that we provide. It has the RA termination but no E marker, so shows RA but no marker. Protocol-wise, we're going to do the same steps, except the tester's going to emulate the E-marked cable messages. So the PD source, which is the DUT, should advertise RP on CC1, makes the connection. It would CRA on CC2, so it knows it's a marked cable. It will source VCONN, then send a cable message to discover its capabilities. Now the tester will receive the SOP prime, and it can respond to that discover. The source is supposed to read the response, and then he should send a source cap that, again, has a max PDO of 3 amps. So that's the other way to do this test. There's a similar test with an unmarked cable. Won't show that, but that's the same idea. Just make sure he doesn't offer more than 3 amps. So it's a safety thing. Okay, power supply operation, also pretty critical for safety. In PD, power supplies can dynamically change power levels. That means really bad things can happen if 2 devices don't follow the same rules. So really, you have to test every aspect of the power supply operation. And a major component of the PD compliance plan is verifying all the different timing windows. This list shows the key parameters that I'm going to focus on. This is where we've seen the most issues with actual devices. Notice it includes both timing and power checks. And while I've noted here these specific test numbers in this third column, we actually check some of these multiple times in several different tests. A lot of these timings are here for safety, right, to make sure you don't overdrive voltage during some transitions. So there's a lot of guard bands that you need to observe. For example, what exactly needs to happen when 2 devices decide to increase the voltage and current? The PD2O spec provides great timing diagrams for all the different power transitions. We're looking at one of them here. You'll note on the right side that these diagrams combine both the logical PD messages that are sent over the CC lines with the internal state transitions for source and sink, as well as voltage levels for VBus. So all the different domains are here. Everyone's probably familiar with the PD handshakes that are used to set up the initial contract, right? When the default source sends his capabilities, the sink then makes a request, followed by the accept. It's not a valid contract until the PS ready is sent and good CRC'd. So every time a port pair decides to increase the voltage, it needs to meet all these underlying timing parameters. Once the request is accepted, a timer starts called T-source transition. That requires that the source wait at least 25 milliseconds before it starts increasing the voltage. that timer doesn't start until the last bit of the good CRC is received. On the accept, there's also an upper limit. It needs to at least start transitioning within 35 milliseconds. So there's a min and a max, 25 and 35 milliseconds. Every positive or negative transition is subject to the T-source settle timing parameter, which, yeah, I guess I missed that one. Yeah. So that's actually supposed to allow him to verify that the new voltage is actually at the requested voltage, plus or minus 5%. So that's a pretty generous window. Finally, our source can send the PS ready. There's another timer called PS transition. This is really an overall timeout, which will expire if we don't see a PS ready within 450 milliseconds. So this is a common point of confusion right here. It specifies a min and a max. So everyone asks, do I have to wait a minimum of 450 milliseconds? No, it's actually a range. But you know, this really means the new sync can decide to time out any time within this range. So I'll explain that in a few slides. Let's focus on VBus for a second. It should be pretty obvious that a device going through compliance needs to stay within these upper and lower bounds when increasing power to vSource new, which is basically, again, plus or minus 10% of the agreed power level. The source needs to become ready within T-source settle pause, which that's 275 millisecond. The source is also supposed to limit his load step slew rate because this can affect communication on the USB bus or really interfere with the USB bus. So slew rate is another important measurement, and on a positive transition, it should not exceed 30 millivolts per microsecond. Here's an example of a device that fails that slew rate test. So we're looking at the final stages of TDA 227, which verifies that the UUT ignores BIST messages if VBus is above 5 volts. So during this test, we first need to negotiate a power transition from 5 volts to 25 volts. Did I say 5? I said 5 volts to 12 volts. Okay. The main goal of this test, we're going to send the BIST message, which he should reject. But we're also going to check all these different timing parameters I just mentioned. So to make that slew rate measurement, it's a pretty simple formula. It's voltage change over time. So 7,000 millivolts over 200 microseconds. That indicates about a 35 millivolt per microsecond slew rate. So that's above the 30 millivolt max. It's too fast, so it's going up too fast. Okay, now let's look at the timing windows for a power roll swap. This is one of the more complex tests for a PD device. The actual message sequence over the CC channel is pretty simple. The source sends a PR swap request. Of course, the device can issue an accept, a reject, or a wait. Ultimately, it will have to issue an accept to pass this test. Then there are the two PS readies, one when VBus is dropped, the second one when the new source has turned VBus back on. So in addition to checking the PD message sequence we see here, we need to also look at all these different timing parameters during the swap. And these are slightly different from the power increase transitions we just looked at. Once the good CRC is sent for that accept, the T-source swap standby timer starts. And that requires the original source drop power and get to VSafe 0 within 650 milliseconds. Plenty of time, right? VBus needs to be fully discharged when he sends that initial PS ready. If we're testing a device that came in as a source, we'll actually check that voltage was at VSafe 0 at 650 milliseconds to make sure he's actually taken voltage down. The termination on the CC is supposed to flip right here from RP to RD on the original source, that is. So he's advertising his intent to now become a sync. If we were testing a sync, we would want to check the iSync swap standby. This is another power measurement where the old sync needs to lower its current draw below 2.5 milliamps, which is like nothing, right? The new source should flip from RD to RP, okay? He needs to show source terminations on CC. Simultaneously on that first PS ready where the old source goes off, that starts the PS source on timer. So here's another place where the spec is kind of confusing. It looks like a min and max, but it really defines a range. It's easier to explain this by looking at the test log. So let's do that. This is a trace from an actual test, the TDB 22312, where the UUT is the initial sync, and then we're swapping to make it the source, okay, from sync to source. In the lower part of the screen is the power tracker view, and if you were fully zoomed out like we are here, you can see VBus going off then back on, which is approximately around where the PS readies get sent. So just to clarify, this PS source on timer I mentioned, it's only used by the sync. He needs to see a PS ready from the new source within this range, or he goes to recovery. So anytime after 390 but before 480, he can legally start recovery. Most devices complete this handshake very quickly, like 4 or 5 milliseconds. So the key is you don't have to wait 390 milliseconds here to send that PS ready. You send the PS ready as soon as voltage has settled at the vSource new. Okay, hopefully that's not totally confusing to you. Another note, we just dropped VBus, right? The USB connection shouldn't reset, even though VBus is gone. That's part of the PD protocol. We don't test this. We don't look at any USB behaviors in PD compliance. Basically, that's tested elsewhere. But if we look closely, we'll see a different problem with this device. The new source should only send PS ready once its VBus is at vSafe 5. Everything looks fine, but if we zoom in on the second PS ready here, we can see the actual slope of VBus coming up. This PS ready is right on top of the VBus on. If you were to do a measurement, you can see he's more than 500 microseconds too early with the PS ready. So actually, anytime we capture a power increase like this, we're going to do this check and make sure that VBus was at vSafe 5 before that PS ready is sent. So that's a real important requirement. While we're on this role swap topic, I mentioned there are message checks that are performed on every test. This is one of the quirks of power delivery. During a swap, notice how the old source takes the sync role. And while the old sync is still responding as a sync. This is something you really should never see in PD, a sync CRCing a packet from a sync. The spec isn't very clear on this, so we've agreed that this field won't be checked in compliance. There are some implementations out there where the source keeps the source role in that first PS ready and others that don't. Okay, now we're looking at the transitions for hard reset. The key parameter with reset is to make sure that VBus stays up long enough for the sync to finish up anything in process. So similar to a power swap timing situation, only here it's called TPS hard reset min, which is 25 milliseconds. So it's a guard band to give the link partner fair warning that VBus is going away. But then it needs to start the transition by TPS hard reset max, which is 35 milliseconds. We also check that VBus gets to vSafe 0 here. Whichever side was the default source needs to wait for T-source recover, and only then turn VBus back on to get to vSafe 5. This is an easy measurement to make in the power tracker. click on the hard reset up in the trace. That's the start point for your measurement. You drag your cursor over to the B point to VSafe 0, and well, you can see that this device fails the PS hard reset min check, where VBus is supposed to stay up for at least 25 milliseconds. We can see the voltage starts dropping after around 22 milliseconds. So that would be a fail. So the Voyager M310C can act as a full 100-watt source on its own, with its own power supply. If a device wants to pull the full PD current from the tester, the full 5 amps, the tester can do that over a standard Type-C cable. But from a sync standpoint, there are 2 tests that require the tester to sync up to 5 amps from a source. So we've designed those tests using a programmable load. This unit is from BK Precision. It's less than $1,000, but it is required for the load tests. We automatically configure it for you over USB for each stage of the test. There's a special load cable that we provide, and the current from the UUT basically flows through the tester, right, to the load box over the load cable. It's all very seamless, designed to work this way, and really this is the only way you can be sure your device can deliver the power it's advertising. So this dynamic load test is one of the trickier tests to implement because we have to correlate protocol traffic with both power and current measurements. The test starts by waiting for the source cap from the DUT, and say it advertises 3 PDOs. We need to check that he can actually source these voltages and actually sync the current that he's advertising. So, for example, we read in his first PDO, which is 5 volt at 3 amps. So as a source, he's got to bring VBus to 5 volts. The tester, acting as a sync, is going to sequentially make 5 requests at equally spaced current loads. One at 0 load, one at 25%, one at 50%, 75%, and another request at 100%. So that one's the full 3 amps. For each request, using the external load box, we're actually going to make sure he can actually supply that current that he stated in the PDO. And that voltage also has to stay within spec. We're going to do this while increasing the load at each request and then do the reverse and actually step down the load. So 10 separate contracts for each PDO. Any deviations would be grounds to fail this test. This is an actual trace from the dynamic load test. So the DUT is the source for VBus. Okay. Below you can see the power tracker is zoomed way out. You can see voltage is initially sourced at 5 volts, and right here the current goes to 3 amps. Okay, so that's the load box. The PS ready is the key point of measurement in this test. That's the source saying your power is ready, so we initiate the load box. You can see we're measuring the current at 3 amps right here. Current is often shown as a negative, which we see here because, well, it's moving in the opposite direction of voltage, so that's normal. If we zoom in on this section of the graph, when the load turns on, you can see some initial droop from the source. This ringing waveform effect is pretty typical for a power supply that's using a switching regulator. But just to show you how tight some of these specs are, you can click on the low point in the voltage graph, and you can see it's dropping to 4.5 volts. That's, right on the threshold of compliance. You need to stay within a half a volt, that's 10% plus or minus, of vSource new. So this is very close, almost half a volt, but not quite. So we would still call this a pass. So we just looked at the DUT operating as a source. Now we're looking at the DUT as a sink after a power transition. The main focus of this test is to verify he adjusts his current draw after agreeing to a new power level. So we're the source, and we're negotiating the power level here by offering 0 milliamps for PDO number 1. We check that he makes a valid request for 0 milliamps, and we also check that he's lowered his current draw below 25 milliwatts. This VBus power packet you see here is another way of looking at the power tracker data. Yeah, so it's a non-graphical version with the power tracker. You see power, voltage, and current as measured at that timestamp in this little event here. And we see that with this individual device, he never really lowers his current, which is why this would be a fail. Okay, it's just stuck there at 53. Okay, PD uses very low speed, low impedance signaling, but there are PHY layer specific tests. CRC checking is done at the PHY layer before passing messages up to the protocol layer. In the test 2.132, we unloaded just a barrage of error conditions on the UUT and make sure he can handle them. In general, you get a bad PD message with a bad CRC, you're supposed to ignore it. We also, check the proper message ID handling and resetting. Pretty rare to see problems with this test, but this shows you what the CRC check looks like on the bus. We established the default contract, right? And then we use get source caps to send errors to a source and get sync caps if the DUT is a sync. They basically need to ignore these CRC errors that you see here. But we see a problem on this last one where we have a symbol error in the message and the device does respond. So that would be considered a fail. There are 3 PHY layer tests in the compliance plan which are really in the electrical domain. These are tests that we don't currently support. Most developers will want to do these kind of measurements with a scope. As long as you can pass these tests in your lab with a scope, you shouldn't have any problems at the workshop. Okay, just a few final points on the Type C compliance. These are the key areas for testing Type C. As I mentioned earlier, this is all still considered dry run at this stage, but it's a top priority for the USBIF to get these test procedures finalized. Obviously, companies want to start shipping Type C end products. In fact, some OEMs already are. Even though they don't have the logo certification, there is a specific logo. There's a specific logo for the power delivery devices. But for Type C, they'll just use the existing logos. So the Teledyne LaCroix platform will support all of the end product functional tests for Type C. And as I mentioned, some of these tests are really complicated. You need to detect state changes that are occurring at the electrical layer. We're directing devices into these different states using the voltage resistance levels on CC. So, this stuff is tricky. The bar is pretty high, and the precision that's needed for these measurements is significant. In addition, there are multiple tests that require PD and USB data traffic simultaneously. So you need to go through PD negotiation and then link up at high speed or super speed plus, go through suspend, resume, capturing the whole exchange. So the Voyager M310C has all of this functionality already. Okay, in the 4.31 Sync Connect test, we'll actually test some of those state machines that control that initial connection process. We're testing a sync here, so the tester is the source. So to start, the sync is not presenting RD. It's considered to be in the unattached state. So from a test standpoint, it's an implied state, not really directly observable. Then from the point the tester presents RP, he's in the unattached source state. The latest release of the analyzer software shows these transitions, time-stamped within the trace. So as soon as the DUT presents RD, he's actually entered the attached wait state. He needs to stay in this state for TCCD bounce, which is a minimum of 100 milliseconds. But then within 200 milliseconds, he needs to transition to the attached sync state. So that's, again, a range, 100 minimum, 200 maximum. How do we know that he's moved to attached sync? There are two steps. He needs to actually sync current over VBus and begin USB transmissions if he supports USB. The DUT needs to stay in this state for at least 500 milliseconds in this test without dropping. There's a source version of this test where we actually check that he actually sources VBus in this stage. So that's kind of the sequence. So he needs to, again, power or make a contract and, again, establish communication. Okay. Then the tester will actually remove VBus, which should cause the logical state of the device to return to unattached sync. And I believe that's the end of the test. Okay. So many of these tests require that we measure voltages on CC1. This specific test I wanted to highlight because here we also have to measure VCONN voltage from the DUT. So we added the CC Power Tracker in our latest software release. This test is supposed to make sure that VCONN gets sourced from the DUT, but as we mentioned, VCONN is not passed through the cable, right, to the analyzer, so it never hits the analyzer. So here's where we needed to create a special cable that connects CC2 all the way through, so we can make sure that VCONN is getting sourced at the full 5 volts, and we'll check that it gets sourced at 5, and then also turned off when devices do roll swaps, all with this special cable. So that is included in the Type C compliance package. Okay. Well, let's see. I've got I have just a couple of more, but it's right at the time I wanted to wrap up here, so we could get to some questions. As I mentioned, all of this testing is done with our Voyager USB analyzer. This was really designed to get you through the next years, really the next 10 years of USB development. The PD30 spec has been in development for a while, and this system will support it fully. So it's definitely everything you need to test your device for USB, PD, and Type C. Okay, so again, that was quite a whirlwind. I will try to address some questions now, so certainly take this opportunity to type in any questions. If we don't get to your question, we'll definitely follow up by email. But first, let's do our Mercury T2C giveaway. Let's see, I believe we have a winner here. We have selected Trey Washburn. Okay, Trey, this is your lucky day. And we will be contacting you to make sure we get all your specifics. Okay, so now let me see if I can find some questions here. Yeah, I often have trouble getting this window to open up. Okay. In the industry, there is conception that LaCroix is covering all of the Type C tests, and when will these be available? The Type-C functional test spec, again, is still draft. We have almost half the tests implemented and are going to be actually dry running those at the next USB workshop. So as I mentioned, you'll want to look forward to that if you're going to the workshop, and you'll see those live and in person. Okay, another question. Why would a source want to renegotiate a power contract? Isn't that for the sink to renegotiate? Well, there's times that a source may want to renegotiate the contract. He can always do so by sending his source capabilities. If his, like say, his ability to supply power has changed, right? So possibly another sink on another port has been disconnected. So now he has more power to source. Anyway, anytime he issues that source PDO, that means his sync partner is required to make a request, and that's something that is actually tested in compliance. So good. Looks like that is most of our questions that I can see so far. Are there any specific tests for vendor-defined messages or VDMs? So the VDM modes are not explicitly tested in the PD. But there are some tests in the Type-C spec that at least look at whether we support those commands properly, including the ability to enter alternate modes. Now, none of the functionality in the alternate mode is checked, but the basic messaging is checked in Type-C. So if you look at that Type-C spec, you'll see a couple of tests, but for the most part, you're going to want to refer to the test specs specifically from these different vendors or these different organizations like VESA for the DisplayPort compliance tests. They have some tests that they're working on over Type-C. Someone mentioned PD 3.0. So that is a pretty exciting topic because PD 3.0 is going to actually be released at the end of the month here. And so our platform will have full support for PD 3.0 down at the message level. There's nothing really at the physical layer that's substantially changing here. It's mostly handling all the new extended message types and some changes to the power rules, etc. So all of that is coming, and we expect to support it fully. And you'll see that definitely in the next few months. Okay, well, listen, I really appreciate everyone's attention and their participation today. Again, if we didn't get to your question, we will follow up by email. It is just about 11 o'clock, so I will wrap it up there. Look forward to additional webinars coming from Teledyne LaCroix, and we'll see you next time.